our last story is out of MIT.
Yes.
It's actually shocking to see some fundamental science coming from MIT. I know Caltech is more well known for that. But credit where credit is due. Famous double-slit experiment holds up when stripped of its quantum essentials. MIT physicists confirm that, like Superman, light has two identities that are impossible to see at once. So, one of the things that we always talk about is there's stuff happening at the size that we are, and then there's stuff happening at the quantum level. And our understanding of these two things is relatively robust, but they don't blend really well.
Yeah.
But it seems like this particular aspect, we're kind of seeing some consistency in both spaces, maybe. But
yeah,
I don't know.
Yeah, exactly. We're basically finding out that like the world really is quantum.
Okay.
And it's really a confirmation on something that we already knew.
Yep.
But it's an incredible experiment in its own right. So that's why I really loved it.
We love experimental design. This looks like it's brand new, July 28th.
Yeah.
So this is, again, this stuff is happening.
This stuff is happening now.
Every week, all the time.
Yeah. So the idea is the double-slit experiment. It's one of the most famous experiments in all of physics. It's something that sort of confirms this duality, this wave and particle picture of light. And it's like, is an electron a particle? Is an electron a wave? I mean, it's like both, but also not both. It's an electron. And a photon, what is a photon? Well, it's a photon. Sometimes it behaves like waves. Sometimes it behaves like particles. Einstein very famously did not like this.
Yeah.
Right?
This is the spooky.
Yeah, he had a lot of problems with quantum mechanics. One of them was the spooky action at a distance, which is something that we're actually going to come to. And then the other one was this idea of like the wave particle duality. It's like, no, the world is just well defined. Right. Like God wouldn't do that.
God wouldn't create ambiguity.
Yes. Yeah. The world is well defined. And like there's, I don't know what you're talking about effectively. Okay. This whole thing started back in 1801 when Thomas Young made the first double-slit experiment with light. He wanted to show the wave property of light. So the idea is the following. You've got a light source, okay, like from here. You create a single slit, like let's say this way.
Yep.
You create a horizontal slit this way. You've got a light source.
Yep.
Back then, he didn't have lasers, right? So he needed a way to create a very like sort of monochromatic like light of the same color and things like that. So he's got a prism that spreads it apart, and then he targets only one color, right? And then you can like be sure that it's just one. Otherwise, white light, there's a bunch of, you're not going to get anything. So he has a horizontal slit in this direction that lets in a specific color of light, and then here he's got two slits, one up and one down here. Okay. And the idea is the light is gonna, if it's a wave, well, if it's a particle, it's gonna like spray like a bullet, and then there's two slits, so it's gonna spray like bullets here, and then if I have a detector, then I'm going to see two lumps of where the light landed.
Right.
If it's a particle.
Right.
If it's a wave, on the other hand, just like how ocean waves spread out and they interfere with each other, the light's going to spread out over here. Then it's going to hit these guys and spread out from these 2 points. And then it's going to create an interference pattern.
Right.
Kind of like the moire patterns that we were talking about last week.
Yes.
Right. Where you have like these fringes going out, and then they create light, dark fringes on the detector, okay? And when we saw these light, dark fringes, you can calculate from the wavelength of light, you can calculate like how far apart the light, dark should be, and they're exactly that far apart. You can do the math and like, okay, it's pretty awesome that like, yep, it's a particle, right? I mean, sorry, light is a wave. Okay. Then comes the quantum revolution. We start understanding that light might actually be a particle. It might be quantized, right? Max Planck uses the quantum of light to demonstrate black body radiation, which is like why stuff that's hot glows the way it does. And then Einstein himself actually uses light being a particle to explain the photoelectric effect, which is how solar panels work and things like that. Okay, so fine. Light can be a particle and a wave, but like you could like sort of justify that by saying that like, you know, even Newton thought light was a particle, and like now we're going back to this idea, maybe there's some like, you know, discreteness in the way that light acts. Then in 1927, George Thomson won the Nobel Prize for this. He did the same experiment with electrons. And he found that electrons also displayed this interference pattern. Okay? So now we're in this spot where now electrons are becoming waves. They used to be particles. Light, that was a wave, is now a particle. On top of that, when people try to theoretically formulate all this stuff, the people like Heisenberg and Schrodinger and Bohr, they come up with quantum mechanics, which now starts having things like the Heisenberg uncertainty principle, right? This idea that like, okay, whatever system I'm looking at, I can't know too much about it, right? If I know the position well enough, I'm not going to know the momentum, so on and so forth. And
which is such a funny thing. I still find that so infinitely fascinating as a mental thing.
Even as a, and I mean, Einstein did as well, right? And he's like, this is crazy stuff.
Yeah.
So then they're like, so then Einstein's like, one of the rebuttals to this double-slit experiment was, okay, like you've got a bunch of stuff going, and so these guys are interacting, right? What if I made the light source so dim that only a single photon ever went through?
Okay.
This whole thing.
Yep.
So it went through one, and then presumably, naively, you would think it would go through one of the slits, and then it would. Right. But if it went through one of the slits, then I should see just two lumps, not the interference pattern.
Right.
Even if I do a single photon, it somehow splits, interferes with itself, which already you're like, what?
Okay.
Why is it interfering with itself? What does that mean?
What does that mean?
And it's creating an interference pattern. Okay. Next question. Next obvious question is to be like, okay, which slit did it go through?
Right.
We only let a single photon through.
Right.
Which slit did it go through? Well, if we start attaching detectors on the slits, then it becomes a particle again, and we see two lumps. We don't see the interference pattern. Okay? So this was already getting weird, and Einstein had an idea. Okay? So Einstein's like, no, this is some weird stuff.
Yeah.
Okay? So he had this ingenious, it's in 1927 Solvay conference. You've seen this photo of the greatest human minds at the time in one spot.
Never to be repeated again.
Right? Never to be repeated again. Honestly, it's never going to happen. Like more than half of them won Nobel Prizes in physics. Just like to be a fly on the wall.
It was the Avengers before the Avengers were the Avengers.
Yeah, 100%. And so he has this idea of like, okay, well, you know, I have this first slit right before it gets to the two. Now, if the light is going and it makes its way to the bottom, then it's going to bump the slit up a little bit upwards, right? Because of the momentum transfer.
Yeah.
Like conservation of momentum, the light got deflected downwards, so the slit is going to bump upwards. Similarly, if the light goes upward, the slit is going to get bumped downwards.
Yep.
So I could instead of watching the light at the two slits.
Yep.
Right.
Yep.
This is Einstein's he's a tough cookie, dude. Like it's like he's not gonna give up because like the problem was I was watching it at the two slits.
Yeah, right.
And then you know it's like, oh well, you messed with it.
Yeah.
Right. But he's like, no, now I'm gonna mess with it over here before it even gets to the two slits.
Yes.
Okay. I'm gonna watch it. I'm going to watch the slit go up and down, and based on that, infer which direction it went.
Right.
And then from there, I can tell which slit it went to.
Right.
And then my interference pattern should still be there, but I'll also know which way it went.
Right.
This is a tough one. Bohr said this was a tough one. So he goes back, and him and Heisenberg, it was basically the dynamic was Einstein would propose a problem, and then Bohr and Heisenberg would stay up all night trying to figure out what was wrong with it. And then they'd come back the next day and they'd have an explanation. This was the explanation. It's a very good one. Bohr said, okay, in order to actually tell whether the slit was bumped up or bumped down, I would have to know very precisely which way the slit was going before and which way the slit was going after, right? I need to know a difference in momentum in order to tell if it went up or down. I need to measure that very precisely. But if I measure that very precisely, if I measure the momentum very precisely, what happens to my position?
Oh, you know.
My position is no longer definite.
Right.
Which means the slit could be here. The slit's position gets fuzzy. Even though I know that it went up or down, but like I don't know where it was when it went up or down.
You know that it's going up the y-axis or down the y-axis, but the actual tick mark on the side, it's fuzzy.
Yes, that's like, fuzzy. That's getting fuzzy, right? And how fuzzy that gets means that you have a pretty wide slit.
Right.
Which means the light could have come from up here or up down there. Which means that this path and this path are no longer equally distant.
Right.
So you're not going to get that interference pattern anymore. The interference pattern is going to get smudged out.
Does
that make sense? And so you can't see, even if you try to do the cheating before the thing happens,
you get to your detector,
the physics knows the cheating is happening.
It's funny 'cause, I mean, does this tie to, I mean, is this kind of the ties to Heisenberg's uncertainty principle?
This is Heisenberg's uncertainty principle,
because the idea is you can only know one of the two.
Yeah.
You can't know both position or momentum.
Yeah.
And like that, it's just what it is.
Yeah, it is just what it is. This is what it is, right? And because of that, like you trying to cheat one step before
doesn't matter.
Doesn't matter because you'll have destroyed the interference pattern already up here.
This reminds me of like video games where it's like the rules of the game are defined. And so like if you try to like walk to the edge of the forest, it'll just like there's no edge of the forest.
Yeah, it'll just make you circle around. Right. Yeah.
So okay, and so I think there's a long history of people asking these very ostensibly straightforward questions.
Where to go?
Right. We have two slits.
Yeah.
We have one singular photon.
Yeah.
We're sending it towards those two slits.
Yeah. Which one did it go through?
And which one did it?
And it's like, don't ask. Right? And Einstein's like, bro, this is our job as physicists. What are we talking about?
If we can't like
so that was Bohr's response, right? Right. And so what these guys at MIT did was, okay, so when we get into that slit problem, right, we're trying to figure out which way it went.
Yeah.
One of the things is you need the momentum to be so precisely determined to understand which way the photon kicked it, right? Mm-hmm. The photon's momentum is very small compared to even if I have a 1 gram mirror, right, or a 1 gram thingy. Mm-hmm. Like that 1 gram is going to have a momentum uncertainty that's like massive because it's so big. Right. Okay. So you need to, in order to actually do this thing where I'm trying to figure out which way the electron went, the thing that is doing the the thing that is doing the pushing of that photon, the thing that is creating this disturbance of the photon needs to be extremely small. And that's what these guys did.
The idea is we were doing this at larger scales.
The slit is massive,
and so the spectrum of your error is so massive because of that.
Yeah, that you can't even do the experiment.
It's not. There's no meaningful results that come from that. Yeah. So we're just saying if we go really, 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 really small, you decrease the band of the possible error, which at least allows you to start to maybe get
at this question, which way did it go? And if I figure out which way did it go, does it really destroy the interference pattern? Right? Because that's what quantum mechanics says. Right. Quantum mechanics says that no matter how small I make the slit, if I try to cheat and get information about which way it went, I'm going to destroy the interference pattern.
Right. Okay.
That's what these guys found. They made slits out of single atoms. Okay. So what they did was they suspended these atoms, which it was either lithium-7, super light, or dysprosium. Dysprosium? Yeah. 162. It's a very heavy element on the periodic table. They suspended these atoms in a light beam. You can do that now, where you have these kind of like these optical tweezers that can
just maintain
hold atoms right at a certain spot in like a little potential well, and it's ultra cold, so they're really cold. Mm-hmm. And then you can have now single photons move through, and they'll interact with the atoms, and then create my interference pattern. And then what I can do is I can turn off the light, and then have the interaction like a microsecond later. Mm-hmm. So gravity hasn't had time to sort of impact it. It's still sort of like there, suspended. But in that fraction of time, now it's no longer in this potential well, so it can start spreading out a little bit. Mm-hmm. And then if a photon hits it, then it'll kick it, right? Because before it was like confined in this well, so it was a pretty rigid slit basically. But now we're getting to this movable thing
where we can measure.
Where it's like I can in principle figure out which atom moved more.
Yeah.
And then be like, oh, it was that one.
Yeah. Of these two sort of
in principle they didn't do this, but they're like, in principle we could have that information. And then all of a sudden the interference pattern disappears, right? And they could tune it such that like the amount of like spread that they were getting in these atoms wave functions was proportional to how much the interference pattern was being destroyed. right? So it's at its very fundamental level. I mean, like Einstein and Bohr couldn't even dream of this kind of experiment, right? Where single atoms are now my slits.
Right. Right.
But that's what they did, and they're getting this beautiful interference, like, and they're getting the knockoff of the interference as they do this thing where if you wait longer, then it spreads out more, then the interference is even worse.
So this is, as we've gone to a higher level of, like, let's say resolution by going super, super small.
Yeah. It's holding up.
It's the wave particle duality is holding true.
Yeah.
Even at the smallest scales we can get to.
Yeah.
Which means that the universe is just weird.
Yeah, it's just a weird thing. I mean, this isn't like the biggest test for quantum mechanics, right? Because there's bigger tests.
For sure.
There's like tests that won the Nobel Prize in physics 2 years ago. That it's like Bell's experiment where you send two particles far away from each other, and then you collapse this one and see if that affected this one, right? It's like looking for correlations far, far away. And
this is the non-locality.
Yeah, this is the non-locality thing. That's really the thing that Einstein was like worried about most. Bohr,
because these things are not discrete.
Yeah. So Bohr remembers. So, like, what happened in the 1927 conference? We basically have these stories about, Einstein did this and then Bohr did this. It's from Bohr. Okay? So like Bohr has maybe like embellished it a little bit, and he kind of, now when we revisit history, it turns out Bohr might have missed the point on what was Einstein's biggest qualm, which is the action at a distance.
I gotcha.
Like Einstein's question was like, it's a very simple thing, right? Even with this double slit experiment, I've got an interference pattern here, and you're saying that it interfered with itself. Fine, I'll even give you that. But then at the end of the day, I only see one particle, right? It's that if I average over multiple particles, then I see the interference pattern, right? Because it's like one particle comes in, it puts it here. Another particle comes in, puts it here. And over time, I'll see an interference pattern. But you're telling me there's a wave function that's everywhere, but then I get only one particle. How does the rest of the wave function know that I'm going to collapse here? Right? Why don't I see two particles?
Right.
It's a very good question.
Right.
It's like, how does this part of the wave function know, okay, don't trigger the detector because the other part is doing it over there,
Yeah.
And so that was really Einstein's main qualm.
Right. Which this is not solving.
This is not solving
at
that.
all.
No.
It's just reconfirming.
This is solving this sort of complementarity thing and showing that it really lasts even at the smallest of scales.
Oh my God.
So there's still a lot more fundamental research to be done. This was done at MIT by the Fedosiev and Ketterbach lab, NSF and DoD funding.
Of course.
Yeah.
All.
Yeah.
Really, really valuable fundamental research. Again, we should fund science.
This kind of stuff is so cool.
I'm trying to dig into this spooky action at a distance. It's so quantum mechanics. Because you always talk to me about this stuff, even in our private conversations.
I'll recommend you a book. It's called "What Is Real." I forget the author, but it's an amazing book. I have a copy. I'll give it to you.
Yeah, no, definitely. Because it seemed, there's always this argument. It's funny. Earlier you were talking about like we're pretty good. The physics stuff, we have a lot of that. We're quite good. The biology people, they'll catch up.
Yeah.
But this area of sort of quantum mechanics, the inability to quantize gravity, whatever. Like all it. There's always the argument that we've already figured it all out. Physics all happened in this time period that we kind of just went through.
But I mean, that's what they told Einstein and Max Planck before they did quantum mechanics, right? So you never know. It's certainly like, I think we're poised for like a lot of cool discoveries both in physics and in biology. I think in biology the tools are now there,
right? Where
it's like we can start doing crazy experiments.
Right.
Before, like with the physics stuff, like the tools. We're only just catching up because electricity and magnetism had just been mastered in the late 1800s, right, with Edison and Maxwell. So then we could have like these like massive electrical apparatuses, and so once electricity and magnetism was solved, then we could go on to this thing. It's like now maybe like once we're getting, there's a lot of possibilities on where this can go.
And just to be clear, it's they're sort of the sandbox that we're playing in is well defined. There are just some corners of it, like this area of quantum mechanics, where we're still just trying to fill in some of the mosaic, but we know where the box is. Yeah. Right? Because we're able to do things like this.
Yeah, we're able. I mean, the fact that we're able to do things, right? Like the fact that we're able to suspend two atoms in a laser. Right. That's because we know a lot about quantum mechanics. Correct. Right. That we can even do that.
Right. Yeah. Right. So it's like I continue to be fascinated by this stuff. 4 really, really great stories this week.